Hey guys, this is Professor Janacek, and I want to explain multiple integration. First, let's compare situations of a single variable with those of several variables. Looking at the functions, in single variable we simply write f of x, but in several variables we could write either f of xy or f of xyz or f of however many variables we may have. The derivative in a single variable is simply denoted f prime of x, but in several variables we have partial derivatives, the partial of f with respect to x, the partial of f with respect to y, or the partial of f with respect to z, and of course the partial with respect to f, the partial of f with respect to however many variables we may have. Integrals, however, look something like this. If we integrate in a single variable, we have the integral of f of x dx. And that is being integrated over the interval from a to b. Now, if we are integrating in several variables, what we have is a double integral or perhaps even a triple integral. Of course, ideally you could go further than that. And the double integral is over a region, which we call R. The triple integral is actually over a three-dimensional region, which here is referred to as D. All right, so let's take a look at how we define double integrals. This is specifically a double integral over a region. We have a double integral of f of x dx. We have the double integral over R of f of xy dA. Notice that differential is of the area A. Formally, a double integral is the limit of a Riemann sum, but those can be rather difficult to compute. I do also want to remind you that our differential is an area. In a single variable, an integral is area under a curve. However, in several variables, we are now looking at a volume that's under a plane, but above a region. And that region, again, is defined by R. So, formally, this is how we define a double integral. But as you may recall from single variable calculus integration, that limits of Riemann sums can be very complicated to compute. Fortunately, Fubini came up with a nice little theorem that helps us out. We'll let f be a continuous function on the rectangle R, which is defined by x and y, where x is between a and b and y is between c and d. Then we can take this double integral over R of f of xy dA and rewrite it as the integral from c to d, and then the integral of a to b of f of xy dx dy, or we could write it as the integral from a to b and then the integral from c to d of f of xy dy dx. Notice that the inside integral has to match up. So we're integrating with respect to x on the inside in this first integral, and of course x goes from a to b. The outside is the y, which goes from c to d. Now we can turn those around and integrate from y and integrate with respect to y and then with respect to x, whichever one works out the easiest. These are referred to as iterated integrals, where we work one integral and then iterate it by following up with another. Let's take a look at an example where we simply evaluate an iterated integral. Let's integrate from 0 to 3, and then from negative 2 to 1 of 2x plus 3y dx dy. Now in this particular situation, we are told which variable to integrate with respect to first. and that is x. So I'm going to keep that outside integral from 0 to 3, If we integrate just with respect to x, we get, what is that, x squared plus 3xy, which we must evaluate from -2 to 1. But don't forget, we still have our differential dy there in the back. All right, evaluating this from -2 to 1 gives us 1 squared minus 3 times 1y. Notice I'm evaluating the x values, not the y values. Minus, now we evaluated at -2, so that's -2 squared minus 3 times -2y. Of course, all of this is now the integrand, and we'll be integrating with respect to y here in a moment. Let's simplify all this inside here. Let's see, what does that give us? That's going to be, oh, oops, and that's supposed to be a plus. There we go. That's going to give us 3 and 6, that's 9y. And then minus 1 minus 4 is 3. Now we integrate with respect to y. That gives us 9 halves y minus 3y, which we will evaluate from 0 to 3. And it looks to be pretty simple at this point. We have what? 27 over 2 minus 9. Oh, guys, you know that's supposed to be squared. Let's square those. Ah, there we go. That's a little better. So that would give us actually, what, 81 over 2 minus 9. Common denominator of 2 gives us 63 over 2. And that is how you work with iterated integrals. Enjoy!